Welcome everybody once again. So we are in our fourth module. We are studying KANIS method. So in today's class, let us see the analysis of symmetric portal frames. That is portal frames with no side sway. So what is portal frames? What do you mean by portal frames with no side sway or symmetric portal frames? See, all these the basics or fundas we have already studied in our second module while studying the slope deflection method of analysis. So I'm not going to the basics of portal frames. We will directly go into the problem. So our given problem is to analyze a given symmetric portal frame. That is portal frames with no sides width. That means your portal frame should be symmetric about y-axis. So the given portal frame is a single bay, single story portal frame. And the supports of the columns are fixed supports. Now the columns are 2 meter. Columns are of span length 2 meter and the beam is of span 4 meter. Now there is a uniformly distributed load of 6 kilonewton per meter. So 6 kilonewton per meter in the span BC. So this is A, B, C and D. Now we need to analyze this beam. So this is similar to the analysis of continuous beams. So step 1, we will find the fixed end moments. Now when we consider the span AB, there is no external loadings. Therefore fixed end moment is 0 for the span AB. So MFAB is equal to MFBA is equal to 0. Now when we consider the span BC, MFBC will be equal to, this is an UDL as I have told you earlier. For fixed end moments, we have to assume all the supports as fixed. Consider the external loadings. So here it is a 6 kilonewton per meter. When you take a section, we know see at the supports there will be hogging moments. That means there will be negative bending moments near the supports. So if it is negative, when you take the section, the left should be anti-clockwise and at the right support it should be clockwise. So at the left, your magnitude for this fixed end moment will be minus WL square by 12 and at the right it will be plus WL square by 12. So we get MFBC, this is B and this is C. So MFBC will be equal to minus WL square by 12, that is minus 6 into L is 4 square divided by 12. So we get minus 8 kilonewton meter. Similarly, MFCB will be equal to plus WL square by 12. We get plus 6 into 4 square divided by 12. We get plus 8 kilonewton meter. Now we will move on to the next span, that is CD. There is no external loadings on CD. Therefore, the fixed end moments in the span CD at C and D will be equal to 0. So MFCD will be equal to MFDC will be equal to 0. We will move on to the second step, that is we have to find the rotational factors. So step 2, find the rotational factors. And we know the rotational factors is equal to minus half of the distribution factor. So for finding the distribution factors, we will consider the joints. So now here we have two joints, right? B and C are the joints where more than one member acts. So we have joints B and C. Now we will write the members. At joint B we have the members BA and BC. At C we have the members CB and CD. Now we will write the relative stiffness. Relative stiffness, we know if the far end is fixed, the relative stiffness is I by L, and if the far end is hinged, the relative stiffness will be 3 by 4 I by L. So here A is fixed, D is fixed. All intermediate support should be considered as fixed support. So everywhere it is I by L. So for BA, the relative stiffness is I by L. So I by 2. BC, the relative stiffness is I by L. Here it is I by 4. CB, the relative stiffness is I by L. All the intermediate support should be considered as fixed support, should be assumed as fixed support. So I by L. For CB, it is I by 4. CD, I by L is equal to I by 2. So relative stiffness is represented by small k. Now we will take the summation of the relative stiffness at every joint. So that is sigma k. I by 2 plus I by 4. We get 3I by 4. I by 4 plus I by 2, we get 3I by 4. Now the distribution factor is equal to k by sigma k. I by 2 by 3I by 4. We get 2 by 3. I by 4 divided by 3I by 4. We get 1 by 3. So we should get 1, that is the distribution factor. Similarly for CB, I by 4 divided by 3I by 4, we get 1 by 3. I by 2 divided by 3I by 4, we get 2 by 3. Now we will find the rotational factor. So rotational factor is equal to minus half of distribution factor, minus 0.5 into the distribution factor. So 2 by 3 into minus 0.5 we get minus 0.3333, and 1 by 3 multiplied by minus 0.5 we get minus 0.1667. Here also it is minus 0.1667. So similarly we get 0.3333. Now step 3 we will find the resultant restrained moments, right? So step 3, resultant restrained moments. So you remember, see, when we consider the second step, since it is symmetric frame, see it remains the same. For B, this point, it is symmetric. Okay, you can see the values everywhere, it is symmetric. So if you find this up to rotational factor for joint B, easily you can mirror it for joint C. Okay, you can copy it as a mirror image. Okay, so for symmetric frame, it is enough to find for one half. Remaining half you can write in a similar manner. Now, resultant restrained moments, we know it is the summation of all the fixed end moments meeting at a joint. So we have two intermediate joints B and C. So we have the resultant restrained moments at joint B and the resultant restrained moments at joint C. So it is represented by MFB. That is, resultant restrained moments at B will be equal to MFBA plus MFBC. Summation of resultant restrained moment at B will be equal to summation of all the fixed end moments meeting at joint B. So that will be equal to MFBA is 0, MFBC is minus 8. So we get minus 8 kilonewton meter. Similarly, resultant restrained moment at C will be equal to summation of all the fixed end moments meeting at C. That is MFCB plus MFCD. So MFCB it is plus 8, MFCD is 0. So we get plus 8 kilonewton meter. Now we will move on to step 4, that is KANIS iteration cycle. Okay, step 4. is KANIS iteration cycle. So we have two intermediate joints B and C. So we will draw one smaller box and one bigger box for joint B, another smaller box and a bigger box for joint C. So we have B and C are, BC is a span. Then we have, here we have A, right? A, and here we have D. So now inside the smaller box we have to write the restrained end moments. So at B it is -8, at C it is +8. Now writing the rotational factors, at B it is minus, for BA minus 0.3333. So for BA it is minus 0.3333, and for BC the rotational factor is minus 0.1667. So minus 0.1667. Similarly, for CB the rotation factor is minus 0.1667, and for CD the rotational factor is minus 0.3333. Now we will write the fixed end moments. We know MFAB, the fixed end moment is 0. M of BC, the fixed end moment is -8. M of CB, the fixed end moment is +8. M of CD, the fixed end moment is 0. And M of DC, the fixed end moment is 0. Okay. Now, we have to find the rotational contributions, right? So since A is fixed support, there will not be any rotational contributions from A to the nearer support. That means our MAB will be equal to 0. Since D is fixed support, there will not be any contribution from the fixed support to the nearer support. So MDC also will be equal to 0. Now we have MBA. So MBA, we have to find small MBA, small m BC, small m CB, and small m CD. So we will write this small m CD this side, and we will write small m BA to the other side. So see, I am writing this here just to show the difference, okay, that is all. Otherwise these both will be very closer. That's why I have taken the another side, that's all. See, if you need, you can extend this line. Okay, if you have any confusion, you can extend this line little more so that you can write without any confusion. Now, okay, now we will move on for the iteration step, that is rotational contributions. We will find the rotational contributions. So we will write it as step 5, okay. So step 5, we will go for rotational contributions. So the four rotational contributions are MBA, MBC, MBA, MBC. See, another simple way to find the rotational contributions are, see, we have already found the rotational factors, okay? So there are only four rotational factors. So there will be rotational contributions only from these four cases. That is BA, BC, CB and CD. Okay. So for what members we have determined the rotational factors. So these members will contribute the rotational contributions, are responsible for rotational contributions. So MBA, MBC, MCB and MCD. So we know the formula for rotational contribution as MBA will be equal to rotational factor of BA multiplied by the restrained moments. It is B, right? So restrained moments at B plus, so the remaining contributions are at B. You can see at B the neighboring joints are A and C. So the rotational contributions will be from joint A and from joint C, that is MAB and MCB. So MAB and MCB. Now this MAB is always equal to 0, right? There will not be any rotational contributions. You can see it in two ways. One is because it is fixed. The other way you can see whether there is a rotational factor for AB. If there is no rotational factor for AB, that becomes 0. Now, the formula for MBC is RBC, that is rotational factor for BC multiplied by resultant restrained moments at B. So, MFB plus what are the neighboring joints for B? So, same. Okay. So, MAB, that is what are the neighboring joints for B? So, MAB plus MCB. Now, so as I told you, this is always 0. So for MCB, the next joint is C. So for MCB, it is a rotational contribution of CB multiplied by resultant restrained moment at joint C plus. So at joint C, what are the neighboring supports? B and D. So it is MBC plus MDC. MBC plus MDC. So MDC is always equal to 0. MDC is always equal to 0. Now MCD will be equal to rotational contribution of CD into joint is C. So resultant restrained moment of C plus, this is the same, MBC, that is for joint C, the neighboring supports are B and D. MDC, so MDC is always equal to 0. Now we will go for iterations. We will go for iterations 1, 2, 3, etc. So iterations 1, 2, 3. So for the first iteration, MBA will be equal to MBA will be equal to RBA, that is minus 0.3333 into MFB MFB is minus 8 plus 0. See, initially we don't have any rotational contribution from C. So initially we will take this small m as 0. So plus 0 we get plus 2.67. MBC will be equal to RBC is minus 0.1667 multiplied by plus 8 plus 0 we get plus 1.33. Now for MCB, RCB is minus 0.1667 multiplied by MFC is plus 8. Sorry, here it is minus 8. So plus 8 plus MBC we have calculated it as 1.33. So 1.33. We get minus 1.56. Similarly, MCD will be equal to RCD is minus 0.3333 into MFC is plus 8, MBC is plus 1.33. We get minus 3.11. Similarly, we will go for the second iteration. So second iteration, see RBA is not going to change. So minus 0.3333. MFB is also not going to change. So minus 8. Only change will be for MCB. So MCB is minus 1.56. So minus 1.56. We get plus 3.19. Now for MBC, it is minus 0.1667 multiplied by minus 8 minus 1.56. So we get plus 1.59. Here it is minus 0.1667 multiplied by plus 8. Now MBC, you have to use this value. Plus 1.59. That is what you have obtained at the last step. Finally, okay. So we get MCB is equal to minus 1.60. MCD is minus 0.1. Sorry. MCD is minus 0.3333 multiplied by plus 8 plus 1.59. We get minus 3.20. So it is some variation is there, right? So we will move on to the third iteration. See, there is a variation plus 2.67 plus 3.19. So we will go for one more iteration. So here it is minus 0.3333 multiplied by minus 8. MCB, you have to use this value. So minus 1.60. We get plus 3.20. So almost closer, right? Now minus 0.1667 multiplied by minus 8 minus 1.60. We get plus 1.60. So closer result. Minus 0.1667 into plus 8. Now you have to change it. MBC is plus 1.60. So we get minus 1.60. So same value. Or minus 0.16, sorry. Minus 0.3333 multiplied by plus 8 plus 1.60. We get minus 3.20, same value. If you want, you can go for two more iterations until you get the closer values. Okay. So I think in the next iteration, you will get the same value. So we will stop with this. So 3 iterations. So these 3 values, iterations for 1, 2 and 3, we will write it in our iteration cycle. So the values for MBA are plus 2.67 3.67 plus 3.19 minus, sorry, plus 3.20. The values for MBC are plus 1.33 plus 1.59 plus 1.60. The values for MCB are minus 1.56 minus 1.60 minus 1.60. For MCD, it is minus 3.11 minus 3.20 minus 3.20. See, just to check, similar values. So, if you are able to find one half, the other half will be same. So, our rotational contributions, see, rotational contributions are, so what is our rotational contributions? Rotational contributions are our final values. These are our rotational contributions. Okay. Now, we will find the final end moments. See, last, your rotational contribution is the values which you obtained in your last iteration. So, that is 3.20, 1.60, minus 1.60 and minus 3.20. So, step 5 is the final end moments. So, final end moments, as I have explained you earlier, this KANIS method is an extension of slope deflection method. So, we know for the slope deflection method, the final moment will be MAB. So, MAB will be equal to MFAB plus 2EI by L into 2 theta A plus theta B minus 3 delta by L. Here there is no delta, okay. So, we are not taking that. So, that means it is equal to MFAB plus 2MAB plus MBA. So, in general term, we write it as MIJ is equal to MFIJ plus 2MIJ plus MJI. Okay, now we will write these values MIJ, MFIJ, 2MIJ, MJI, and finally MIJ is equal to MFIJ plus 2MIJ plus MJI. That is 1 plus 2 plus 3. This plus this plus this. Now see, our diagram is like this, right? A, B, C, D. So, we will have, for MIJ, we have MAB, MBA, MBC, MCB, MCD and MDC. Okay. So, now what is MFIJ? This is nothing but the fixed end moment which we have obtained in our first step. So, MAB it is 0. MAB, the fixed end moment is 0. MBA is 0. MBC is minus 8. MCB is plus 8. MCD is 0, 0. Now, what is 2MIJ? That is 2MAB. Okay. So, we know MAB is equal to 0. So, here we get 0. Here it is 2MIJ is BA. So, what is 2MBA? MBA is plus 3.20. So multiply by 2, we get plus 6.4. So plus 6.4. Now here it is 2MBC. So for BC it is plus 1.6, multiply by 2 we get 3.2. Plus 3.2. So remaining things also as you can do it in a similar way. It will be just the symmetric of this. So minus 3.2 minus 6.40. See, you can write this only because it is symmetric. Okay. If you have writing the one half, the other half will be similar. Now MJI means it is MBA. So it is MBA. MBA is plus 3.20. Plus 3.20. Here it is MAB. So MAB is equal to 0. Next MCB. Because JI, right? JI. So it is CB. MCB will be equal to, MCB is minus 1.6. Here it is MBC. So similarly you can write. So MBC is plus 1.6, right? Plus 1.6. So it is plus 1.6. 0 minus 3.20. 0 minus 3.20. Now in order to find the final end moments, Mij, add all these. So 0 plus 3.20 we get plus 3.20. 0 plus 6.4 plus 0 plus 6.40. So it is kilonewton meter. Minus 8 plus 3.2 minus 1.6, it is minus 6.40 kilonewton meter. So other three will be similar. Okay. So plus 6.40 kilonewton meter. Now minus 6.40 kilonewton meter. Minus 3.20 kilonewton meter. Okay. Now we can draw the bending moment diagram. Okay, before drawing the bending moment diagram, we have to draw the simple beam moment diagram, right? So step 6 will be simple beam moment diagram. Step 6 is a simple beam moment diagram. So simple beam moment diagram we know only for when there is external loadings, right? There is external loadings only. Here there is external loadings only for the span BC. So for the span BC we have an external loading of 6 kilonewton per meter. 6 kilonewton per meter and the span length is 4 meter. Therefore, this is a UDL. So we will have a parabolic shape and the magnitude will be WL square by 8. So 6 into 4 square divided by 8. We get 12 kilonewton meter. So just 12 kilonewton meter. This is our simple beam moment diagram. Okay, so first of all we will draw the simple beam moment diagram. Then we will superimpose it. Okay. So drawing the simple beam moment diagram. So here there is an UDL, the magnitude is, it will be a parabola, right? The Simple beam moment diagram will be a parabola. And the magnitude is 12 kilonewton meter. Now we will we will mark the final end moments. So we know the final end moments for AB, it is plus 3.20, right? For AB it is plus 3.20, that is clockwise, 3.20. Then for BA it is plus 6.40 clockwise. So when you are drawing the clockwise, so plus 6.40. Then for BC it is minus anti-clockwise. So I will draw separately. So okay, for AB it is plus, so clockwise 3.20. For BA it is plus 6.40. For BC minus 6.40. CB it is plus 6.40. So clockwise, okay, plus means clockwise, minus means anti-clockwise. CD it is minus 6.40, so anti-clockwise. DC it is minus 3.20, so it is anti-clockwise. Okay, now see it is clockwise, so it is anti-clockwise pointing towards the right. So 3.20. So 3.20. Now here it is clockwise pointing towards the left, 6.40. 6.40 kilonewton meter. So 6.40 kilonewton meter. Okay, so this is our net bending moment here. Now for the span BC, it is a 6.40 anti-clockwise, so pointing upwards. 6.40 kilonewton meter. And 6.40 kilonewton meter pointing upwards. 6.40 kilonewton meter. So net bending moment is like this. So that means from this to this point we have a hogging bending moment, from this to this we have a sagging bending moment, and from this point to this point again we have a hogging bending moment. Now here this minus 6.40, that is anti-clockwise pointing towards the right. So 6.40 kilonewton meter. And at D, this anti-clockwise 3.20 pointing towards the left. So 3.20 kilonewton meter. This is our net bending moment diagram. So this is our bending moment diagram. Now how will we draw the deflection diagram from this? So the deflection diagrams are, so here there is a change from positive to negative, right? Negative to positive. So first of all, we will draw for the span BC, sagging and hogging, right? So after this, it will be deflecting like this. Okay. There will be a point of counterfluxus at this point. So this is our deflection diagram. Thank you. That is all for today. So in the next class, we will see how to analyze frames with the side sway. So this is frames without side sway. Okay, with no side sway. That is a symmetric frames. Thank you.